In this video, we'll be going over how to use the files produced by Field of View's GeoSnap PPK system to produce a corrected trajectory and to interpolate events using EZSurv post-processing software. One of the first things that we want to do is make sure that the number of events recorded by the GeoSnap PPK match the number of images captured by the camera. In this case, we have 234 events, and when we open the image folder, we can see that we have 234 images. If there is a mismatch in this number, this needs to be addressed before starting the PPK processing. Next, we're going to go into EZSurv and go to Tools, Mapping System, Selector. By default, when you first open EZSurv, it'll have WGS84 as the current mapping system. For this data set, we're going to use the North American datum NAD83, and we're going to use the UTM projection. This data set happens to be collected in Zone 16 North. Normally, we would also go ahead and choose the antenna model for the GeoSnap PPK or the rover, but in this case, the offsets associated with the L1 to antenna reference point offset will be accounted for in a different location, so we're going to keep the antenna model as none. Next, we're going to drag in the .bin file, which is the raw GNSS data collected by the GeoSnap PPK. EZSurv is reading this file, analyzing the data, and preparing it for further processing. It will also put some additional files in the same directory as where the .bin file came from. We can see that the little vehicle icon is associated with this file, indicating that it's a moving file and that it's not static. We can see that it's got both GPS and GLONASS data. The R means GLONASS in EZSurv. We have 100% coverage, and the data was captured at a 20 Hz rate. The serial number is embedded in this raw file so that the serial number version of EZSurv can be used to process this data on any computer. Next, we're going to go ahead and click Start Automatic Processing. One really nice thing about EZSurv is that it will automatically determine the closest continually operating reference station available and download the RINEX data or the raw GNSS data for that core station. In this case, the PRDU station is being used. It has both GLONASS and GPS data, which is great, and it is now processing the trajectory. So go ahead and pause the video and come back when it's done. Okay, this process took just a few minutes, and we can see the summary of the results here. The continually operating reference station was 2.2 kilometers, which is nice and close by, which helped get us a 100% fixed result. Every once in a while you'll see a small percentage of float solutions, likely because perhaps the operator walked past the antenna at the beginning or the end of the flight, which isn't a problem. If we have a high percentage of float solutions, it may be because the continually operating reference station data wasn't very good, in which case you'd want to select a different base. We can visualize the results of this by clicking this Display Plan View button up here. Here's the location of the base, and here is the flight path. You can see what we mean by trajectory. It's this green line here. It's the path that the antenna followed, and each one of these individual dots represents an epoch or an individual position that was determined. As the drone is moving faster, these dots are spaced out, and as the drone slows at the corner, they get closer together. The next step that we want to take is to interpolate these positions to where the actual images were captured. So in the event log, we have precise time data so that we can know where along this line each individual photo was captured. One thing that we have to keep in mind is that this is the position of the antenna as the drone is flying, and ultimately we want the position of the camera to create the geotags. So one thing that we're going to do is have the offset from the camera to the antenna available to us for this next part of the process. So we're going to go to Tools, Event Interpolator, and then we're going to select the event log. We're going to select Configure Event File Format. The delimiter is comma. There are two headers, and the second one represents the column name. We're going to drop down this menu and select GPS time of week, and the format is in seconds and not milliseconds. We're going to hit Save. Next, we're going to go to the Antenna Offset tab, and we're going to copy and paste these values. These values are valid for a field of view designed fixed mount for the Sony a6000. In a different video, we'll go over how these were precisely calculated. We used a combination of a CAD model of the drone, the mount, and the camera, along with information about the focal length of the lens and knowledge of how the nodal point is calculated. Also, information about the antenna offset from the L1 phase center to the antenna reference point. So we'll go ahead and go to the Output tab, select Format as CSV, and then we're going to order these individual items in a way that's compatible with some of the software we're going to be using this output in. Both Pix4D and Agisoft are looking for the image file name to be at the first column. So we'll go ahead and put that up there. The typical US convention is to put latitude first, then longitude, or the Y coordinate, and then the X coordinate. Then we're going to go ahead and put the ellipsoid height, and then we're going to put the standard deviation, which is an accuracy estimate, in the Y, the X, and then the height. So we're going to unselect these other ones. It's possible to output a file with them included, but they're not necessary. Going to make sure these are selected. And we're going to hit OK. OK. Well, before we do this, though, we're going to actually save this profile. If we save a profile, we don't have to take all these steps the next time we do this. So the process will be much faster. Since these offsets are specific to a certain configuration, we're going to indicate what type of setup we had and also the lens that we used. Hit OK. And we can hit OK here, and it will ask us to specify the directory that the images are in. It will do two things. It will make sure that the number of events in that image directory are the same as the number of events in the file, and it'll also grab the first image name and apply it to the file. So we can open the output here. It'll create two files. One is called the events header, and the other one is the events. The events header file provides information about the processing, the files used, the offsets. So this is very good, so you can look back and see exactly how it was processed. The actual events file looks nice and clean. We have the image name, the coordinates, and the standard deviations. Now these are in meters, so you can see that the estimated accuracy is quite good. Now this file is ready to be imported into a software like EZSurv, where you can specify the column order and what fields they are. Pix4D requires a specific order and format, and so in order to make it compatible with Pix4D, we just need to quickly add 3 columns here. And Pix4D is looking for omega, phi, and kappa angles. Of course, the GeoSnap PPK doesn't have an IMU and doesn't actually capture these, but in order for it to correctly read the data behind these fields, we need to just put something in there. So we can just go ahead and put zeros and apply them to all the results and hit save. Now this file is ready to import into Pix4D. Can also be used in EZSurv and will provide the corrected and accurate geotags necessary to produce a high quality photogrammetry project.